Hello everyone, my name is Maxence Rube. I'm a PhD student from the University of French Guiana, currently working at the University of Bordeaux, France. I would like to thank the IEEE Sensors Conference organizers, particularly in this troubled time. I would also like to thank the chairman of this presentation. And today I'm going to present you my work about a dual love wave and impedance-based sensor, and particularly on the topic of response enrichment. Interdigitated transducers are ubiquitous in modern microsystems, but for really different and specific goals. There are mainly two of them, the planar capacitances that are used for electrochemical impedance spectroscopy and electromechanical system. So all those ultrasensitive sensors exist, but a more challenging step is to take those sensors in real detection condition with protocol compatible with the field reality and for representative samples. With this new step comes a lot of difficulties because ultrasensitivity leads to a wide variety of physical parameters influencing the sensor. So a few simple solutions exist, such as the inhibition of the sensor sensitivity through design, or the use of a reference unit. But with this solution come two drawbacks. The first one is that an inhibition is rarely perfect. The second one being that the reference unit is as effective as sensors are identical, which also rarely occur. But for us, the most important drawbacks is the loss of the shared physical parameter influencing the response without external sensors. So the goal of this work is to explore the possibility of decorrelating and estimating the dielectric and mechanical effect on a love wave sensor in liquid medium. To achieve this goal, we're going first to present the experimental setup. So I'm going to describe the love wave delay line and the liquid test cell operation. And then I'm going to present the experimental measurements and the liquid sample that we will be using. From there, I'm going to separate the capacitive response of the sensor from the electroacoustic response. And I'm going to do a brief synthesis of each case just to conclude. In this figure, you can see a simplification of the love wave sensor next to the real sensor. So it is made with two transducers, which are interdigitated. There are 88 fingers and a presented wavelength of 40 micrometer. There is also a 6.4 micrometer thick silica guiding layer, which has the purpose to separate and conduct the acoustic wave, but also to protect the transducer from varying directly in the contact of a solution, which would be, of course, disastrous for the response. So here we really have two capacitance per sensor. There is also a PDMS microfluidic cell, which allows us to protect the electrical contact of the sensor, and also to make sure that there is the same solution height everywhere in the surface of the sensor. The method is quite simple. We use joacasting of 100 microliter of 6 different solutions. We do a full cleaning between each measurement. The sensors are tested twice for each solution, and we pick 3 sensors from the same technological run and roughly the same characteristic. We also do a wideband spectroscopy using a copper maintenance planar 304 VNA, and we estimate the S parameter. Then we calculate the Z matrix equivalent and the presented capacitance using the following equation. The solutions tested are presented here with indicative physical parameters. So we use acetone, ethanol, deionized water, and 3 mixture of polyethylene glycol with increasing volumic ratio and aqueous solution, so with deionized water. We chose those 6 solutions for 2 dynamics. First is to look at acetone, then ethanol, then dehydrated water. There is an increase of the permittivity and also an increase of the viscosity and the density, so the mechanical parameters. The dehydrated water and the aqueous polyethylene glycol mixture, also with increasing volume ratio, present an increase of the mechanical parameters, but a decrease of the dielectric parameter. So it will be really interesting to compare those 2 dynamics. In this figure, you can see the impedance presented by the sensor versus frequency. So as you can see, the response is mainly capacitive from 1 mega to approximately 90 megahertz. And this is really interesting because this means that to separate the dielectric and the capacitive response of the sensor, we could possibly use different frequency. So it is known that for this sensor, the acoustic generation occurs at 110 megahertz. So if we look at lower frequency, we suppose that we will have only the dielectric response. In this figure, we plotted the effective capacitance inferred from Zen11 measurement versus frequency and for various solutions. As you can see, with an increase of permittivity, there is an increase of capacitance, which was expected, of course. But what is really interesting is that there is an optimal frequency, a spot where the capacitance seems to be more stable and around 10 megahertz. So this is a frequency that we are going to use to plot the following figure. This figure shows the capacitive measurement synthesis, so the synthesis of the capacitance variation per liquid sample using as a reference the bar device at 10 megahertz. As you can see, an increase of permittivity increases also the capacitance, as we just showed, but this occurred despite difference of mechanical parameter, which is really interesting. From there, we're going to do the joacastic response of the sensor. So here you have the S21 response at the acoustic resonance frequency at 110 megahertz. As you can see, for an increase of permittivity, there seems to be an increase of the noise level. And this is due to the dielectric couplings. There is 2 of them over the transducer, which influence directly the S11, and from the input to the output transducer, which also influence the S11 and the S21, especially the noise level. So, to separate those response, the dielectric coupling from the acoustic response, we are going to do a love wave, just a filtering, a simple filtering. This is really simple to do because the acoustic wave celerity is way slower than the electric coupling. As you can see here, you can see a lobe of acoustic wave, majority of acoustic wave, around 2 microseconds. So what we are going to do is simply suppress the S21, except from 1.3 to 3.5 microseconds. This will suppress the electric coupling, which can be seen at around 0 microseconds. But also it will suppress the triple transit or the acoustic reflection, which can be seen after 4 microseconds. After the time gating, we can retrieve this kind of spectre, which is the spectre without dielectric coupling and acoustic reflection. This allows us to extract the first electroacoustic measurement parameters, which is the phases. As you can see, for an increase of the mechanical parameter, there is also an increase of the dephasement. which was expected and is really well documented. We can also look at the attenuation for the electroacoustic response. And as you can see, there is also an increase of the attenuation of the S21 parameter at 110 MHz, following an increase of the mechanical parameter of the solution. And this despite the variety of dielectric parameters. In conclusion, we used a quartz substrate-based love wave device of both a dielectric and mass viscosity sensor in liquid medium, and it is possible to decorrelate each mechanism. This method will be extended in further work and optimized with a sensitive layer such as porous titanium. We are currently searching for an optimal guiding layer, allowing the best compromise for the best dielectric and the best acoustic sensing using finite element method. Thank you for your attention, and if you have questions, I'll be glad to answer them.